Okay, so we were talking about equipotential and potential voltage. So again, you have a distribution of charges, which happens like in any living organism, right? We have a lot of distribution of charges. Everything is electrical in nature inside us. But what you see here are the equipotentials. So what it means, here you have 30 volt, for example. So you have to imagine it's like a hill. And here it's going to be negative, like negative 2 volt. So it's like a throw. So what does it mean, 30 volt? It means that if you place 1 coulomb of joule at that location, it will have a potential energy of 30 joule relative to very far. So with distribution of charges, we're going to say that very far, that will be the ground, the potential equals to 0. Okay, so it's always, potential energy is always relative to a reference level. So if you have a charge Q placed at this equipotential, it will have an energy of 30 times Q joule relative to far away. So you see the potential energy here is positive. So it means it's not happy. Okay, so it means if you let go, the electric field will do work on the charge to bring it downhill. You see that the electric field here is like a conservative force. It wants to lower the potential energy as much as possible. The electric field here, so it's a vector field, and the electric field is always perpendicular to the equipotential. You see, it's always perpendicular. Now, here you have negative potential, which means, let's say you have negative 2 volt. That means if you take 1 coulomb of charge at that equipotential here, at that location, it will have a potential energy of negative 2 joule relative to infinity, to the ground, to very far away. If you have a charge Q and Q is positive, so then the potential energy will be negative 2 Q, 2 times Q, okay, relative to far away. So it's potential energy, but the potential energy is negative, which means it's in what is called an energy well. Okay, so it means if you want to take it out of the well, you have to do work because it's very happy there. It's bound to the negative. It wants to go even closer to the negative. So if you want to take it uphill, so it's like going uphill when you are biking, you have to do work against gravity. Here you have to do work against the electric field. Okay, so that's how it works. So usually you do that with a code. You have to do coding, computer coding, right, to find the vector field and the equipotential. But anyway, now if you have a negative charge, everything is opposite. So negative charge placed here, it's going to be very happy, right, because it's close to the plus. So negative charge wants to go up the potential. It wants to go this way. Okay, it's the opposite. Okay, so that's just a review. So negative potential is binding, meaning you have to do work to unbind. Okay, so we did that, and then, okay, we did all that. So remember, mathematically, the electric field, okay, the electric field is the slope of the potential. So in a 3D, in that case, the electric field is the steepest slope. So it's like if you have water flowing, you see the water will go always through the steepest slope. So the electric field at a given point, it's the steepest slope of the potential. So here you have a function here, and you can find what it's called mathematically a gradient, and a gradient will find the slope. So anyway, the electric field derives from a potential. And to find the potential, you have to integrate. So derivative, integral, they undo each other. So if you have the potential, you take the derivative, you get the electric field. If you have the electric field, you take the integral and you get the potential. Okay, so any restoring force derives from a potential. Okay, so it's important for chemistry. We did that. And then we talk about corona discharge. So in air, so air is a good insulator. So you can charge a Van Graaff generator. It's not going to be discharged up to a point. If the electric field is going to reach 3 million volt per meter, okay, that will be the breakdown of air. So now the electric field is so strong that it will break down, meaning all the charges here will make their way to the ground or to a connection to the ground. And that's when you're going to have a spark. Okay, it's called corona discharge. If you get to 3 million volt per meter. So Van Graaff generator are safe because even though the voltage is very high, you don't have enough current when there is a discharge. Okay, so we can do the computation in that case. Let's say you have a Van Graaff generator. That will be the size, 20 centimeter. That will be the voltage. The goal is to find how much charge it's holding if you want to do the computation. Okay. Wake up, wake up. So we have Van Graaff generator. Let's say it's charged positively. Okay, so the voltage is 600,000 volt. Okay, that's a given. The size is, I forgot, 20 centimeters. Okay, 20 centimeters. Is that the size or do they want, okay, oh yes, how much charge? Okay, so you see that voltage here, that will be the voltage here, but it's also the voltage inside. Okay, so inside the conductor, it doesn't matter if it's empty or it's solid, the voltage does not change. So if you look at the voltage as a distance here, okay, it's going to be constant, okay, up to reaching the radius. So same voltage, and I explained why last time. And then as you move away, it's going to go as 1 over R. So the equation is the voltage equals K, which is 9 times 10 to the 9 times the charge here on the Van Graaff, for example, over the distance R. And it works also at that location here. So first the voltage is going to be very large, and then it's going to decrease as 1 over R. If you do it in a 2D or in 3D, you see, remember you have something like this, right? Yeah, I don't know what it's called in geography. It's like a special hill and it's flat here. You have a plateau. It has a name. I forgot. I forgot what it's called. But that's the idea. So to do the computation, not curb your enthusiasm here. A mesa? Mesa? Do you know in geography how it's called when you have something like this? Masa, mesa. Huh? Meset, it's called? When it's flat at the top. Meseta. So I think masa in English, what is it? Huh? Matza? Oh, plateau? Oh, you say plateau? No, there is a special name for this structure here. Masa. Okay, it's just my pronunciation. Masa. Like in Wyoming, you have one special one where it's all like all around. You have like strips, and they say it's because there was a bear that scratched it. It's a special. Okay. Let's go back to physics. But anyway, it will look like something like this, like a masa. Like the whole thing is that like just the very top of the very flat. Yes, exactly. Massa, M-A-S-A?
Yeah, M-E-S-A.
M-E-S-A. Mountain. Yeah. See, you learn a new vocabulary. Okay, something like this. There is one special in Wyoming, very famous, but anyway, it looks like something like this. So anyway, so that will be the potential for Van Graaff, because inside here, you see that will be R. The potential is not going to change. Okay, potential not changing inside, and then it goes down. Okay, so the goal here is to find how much charges you have here, you can hold. Okay, so you just plug in. So you have the voltage is 600,000. Okay, equals 9 times 10 to the 9 Q, and then here you have 0.2.
Like 1.3 repeating, but into the negative
1.8 times 10 to the negative 5 Coulomb, right? Which is 13 microcoulomb. So it's very small. And because it's very small, it won't kill you. So if you touch it, okay, this is 600,000 volts, fine, but you have only, that much coulombs going through your body. It's not going to kill you, and your heart will be okay. Okay, so that will be fine. Okay, now the interesting thing I told you is that the electric field is 1 over r squared, right? So if you are looking at the electric field now, at a distance of r, inside, what's the electric field inside? 0, right? You cannot have an electric field inside a conductor, and all of a sudden, then it goes down 1 over r squared. So the potential is k Q over R. So that will be the potential relative to very far away, which is the ground. Okay, far away means the ground. This is the ground. So then the electric field goes down as K Q over R squared. So how do you go from one to the other one? If you have the voltage, you take the derivative. Okay, so dV over dr, and you get the electric field. And if you have the electric field to go to the voltage, you have to do the integral. So if it's in 1D, it's easy. If it's in 3D, it's not easy because the electric field is a vector. So that's why you have to use a gradient, because you go from a vector to a scalar. So have to do the gradient, the operator. But if it's in 1D, then it's fine. So what you see here is that what you see is that the voltage, okay, it's going to be the electric field times R. Do you agree? Okay, so for the same voltage now, okay, so imagine now that I'm going to erase that. I have another Van Graaff generator, but a smaller one, because I don't have the money to buy a big one. I'm going to buy a tiny one, an itsy bitsy tiny one. Okay, so the radius is less. Do you agree that the radius is less? Okay, so smaller. Okay, so here we have V equals E times R if we are located here, the surface. And now I'm going to connect them together. Okay, so I'm connecting together with a conductor, like a wire. So what's going to be the voltage here? when two conductors are connected to each other, they're going to have the same, the same voltage, right? So if this person here, for example, has the same voltage, conductors, when you connect them together, they will get the same voltage. So if that person here is isolated from the ground, she will be at a voltage of 600,000 volts, right? But it's fine because it's not the voltage that kills. She will be fine. They're very happy. So everything, all her body or his body will be at 600,000 volts. This is at 600,000 volts. Okay. The charge will not be the same. Okay, because now the voltage is the same. Do you agree? So we have the voltage is the same for both. Here we're going to have an electric field E sub 1, and here we're going to have an electric field E sub 2. Agree? Okay. How is the electric field? We already know that, right? It's radial. You have an electric field here. It's radial. It's like a point charge. And we have an electric field here, E2. Agree? But it's the same voltage. Are you with me? It's the same voltage. So you have, for the first one, E1 R1, and for the second one, E2 R2. So electric field times the radius. So we have E1 R1 equals E2 R2. Do you agree? Are you with me? Okay, so what do you think is going to happen to the electric field? Which one has the largest electric field? Okay, so you have E2 over E1 equals R1 over R2. So R1 is larger than R2. So which one is larger? E1 or E2? Because you see it's inverse. E2, very good. Okay, so it means that when you are charging a conductor, the one with the smaller curve, okay, the sharp curve will have more electric field, has more electric field. And that means, because an electric field for a conductor is sigma over epsilon 0. Remember? So that's the charge density. So you're going to have more charge density when something is very curvy. Okay, so sharp edge means more electric field, means larger density. Okay, so that's one way to show that. So that's why it's an issue when you have the high tension lines, and you see here those things here, you see sharp, they are very sharp. So you're going to get a very, very high electric field, very large electric field. So you're going to get to the maximum electric field you can have inside air, and it's easy to get a discharge. When you get a discharge, you lose energy. So that's a problem for the electric company, right? So the Benjamin Franklin, he came up with the, when you have a building, you have a special road here, right? Okay, so what's happening here, it's connected to the ground. So here you have a very, 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 very high density. So maybe you're going to have some charge as well here, because here you have a cloud with minus, 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 minus. So you have a strong electric field. And you also have plus here. So all that, you have an electric field, right? You're going to have an electric field between the cloud and here. That will be the electric field here, from plus to minus. But the electric field here is not strong enough to have a breakdown. However, between here and there, the electric field is going to be so strong, then the breakdown will happen here. Okay, so you're going to have lightning, boom, 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 through here and not through there. And that will be connected to the ground, and you have a connection to the ground. So that's how it works. A lightning rod, that's what it's called, lightning rod. Isn't that cool? So for example, if you have something like this, you're going to have more electric field here, larger charge density. So you're going to get a quick discharge between them. So if you charge a Van Graaff generator, it will go bzz and then connect it to the ground. So you see larger charge density here when you have a sharp corner. So this is a example to connect to history. So I don't know if you know the story. It's a very famous story. It's during the Nazi Germany, 1930s. So there was this German company, and they built the largest airship in history. It's called a Zeppelin. It's called a Zeppelin because the German company were very good at building stuff. Yeah, exactly. That was the issue. Exactly. So Germany are very organized and they're very good at building stuff, which could be a problem, of course. But anyway, Zeppelin, okay, they built that huge airship and they used that as a transportation airship. So they were transporting people from Germany to New Jersey, and it was the Nazis. So that's why on the tail you had the Nazi cross swastika. Okay, that's what you had here. So it was also a way for propaganda, look, we are Nazis, but we are so good at building stuff. So anyway, and as you said, the issue was it was full of not helium, which is lighter than helium. Hydrogen, very good, right? So because it was lighter, it was more efficient. You don't use as much fuel because it's lighter, right? So full of hydrogen, very flammable. So when it got to New Jersey, here you had a pole. So there was a pole. And because it was a thunderstorm outside, you have a lot of friction happening. So because of the friction, you have transfer of charges. So for example, here it could be positive. So you have a distribution of charges because even though this was not a conductor, if you have two insulators, you rub them against each other, that could be plus, 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 plus. Getting to here, this is a conductor, so all the minus from the ground, they come here, and you have a very strong electric field plus the edge, it's sharp, very strong electric field here, larger than 3 million volt per meter, and you have a breakdown. So you have a spark, and because you had a spark, it got fire, and I think like 36 people died. So some people say, oh, some people attacked because they were Nazi, but it's really the physics. So that's for the story. If you're interested, you can watch the video. But the point is that an electric field is like a restoring force. It wants to lower potential energy. It wants to bring the plus with the minus. And when it succeeds, it's called a breakdown. Okay. Okay. So the calculus part now. So I'm not going to detail all the computation because it's done in your book, and you should do it if you're an engineer because it's good practice. So instead of having a discrete distributions, so Q1, Q2, Q3, Q4, now you have a distribution which is continuous. So for example, in that case, maybe it's over a volume. So little dq, for example, it's going to be rho, the volume density, times the little volume here. If you have a distribution over an area, you use sigma. If it's over a line, you'll use lambda. So it's like before, except now it's much easier because the voltage is a scalar. So you don't have to worry about the x component, the y component, the magnitude. Okay, so it's much easier. So each little dq, it's going to generate its potential dV, which is small, okay? Depending on dq, you use that equation. So when you add up, you need to use an integral. Okay, so you have to scan through the inside to get the voltage at that point P from all the little dq inside. So it's a nice application, calculus, because Newton invented calculus. So it's just for physics, right? for nothing else. So example, that will be a ring. Okay, you remember the ring. So now you take the dq and you find the dv at that point. Okay, you want to find a variable of integration that will be x is fixed, a is constant. So you just have dq, and that's what you get. So this one is a very easy integral. You just go around the ring. Okay, now if you take the integral, if you take Wolfram alpha, because I will not know how to do it without Wolfram alpha. If you take the integral, but if you are in calculus, you should know how to do it. If you take the integral, not the integral, the derivative. If you take the derivative, you should get what? If you take the derivative of the potential, you should get the field, right? The electric field derives from a potential. So if you ask Wolfram alpha, find the derivative, okay? What you should get is, so let's look at the equation sheet. You should get this. Do with Wolfram alpha. Okay, you see, electric field of a ring. So you can do that. You can go on Wolfram alpha and you take the derivative. Yes.
Question for the ring, it doesn't have the square root that you have up there on the bottom. It says k times q over x squared plus a squared. There's
Oh,
supposed to
yeah.
be a square root there.
I think it might be a mistake then, you're right. Mm, yeah, it's a mistake. It should be the square root. Yeah, there is thank you. There is square root here. So they did a mistake. Thank you for bringing that up. Okay, so let's see. Ring, they are missing the integral here. You see, you can fix that. There is a, not integral, the square root. Okay, and if you take the derivative of that, you're gonna get this one. From the 1/2 at the denominator, you're gonna get to the 3/2. Okay, so you take the derivative, you can do that with Wolfram alpha of this, you get that. So they did a mistake here, you need the square root at the denominator. Okay, and then you see, you remember you had also the plate, the disc, and here you have all the steps, but you start with a ring here with a charge dq, and you go from here to there. You're gonna scan through, and that's gonna give you this answer here. Okay, so that voltage here is always relative to very far away. So very far away, the voltage equals to 0. That will be the voltage as you go closer to the disk. So the voltage will be the work that you have to do to bring a 1 coulomb of charge from very far away to very close. And that's the equation that you get. And you see, you can find the voltage of the disk if you do z equals 0. So it means z equals 0 at that position here, you're going to get a constant k sigma 2 pi r. Okay? The electric field, you remember it was sigma over 2 epsilon 0 for a disk. And then you can, so this is a double integral. And then here it's a line. So you can find the voltage here and you do the calculus as well. Is that clear? You take a little dq, you have the distance, and you just scan through, and you add that. Again, it says if you want to look at the details, which is interesting, it's textbook 23.10. Is that clear? So you're using your integral skills. And so again, I found that it's a summary. So if you have a point charge, that will be the electric field. To find the voltage, you take the integral, okay, you're going to find that. Or from the voltage to the electric field, you take the derivative. For a dipole, you see this is in distance cube. The voltage is distance square. Okay, so you go from here to there, you have to take the integral. You can ask ChatGPT how to do it. The charge disk, infinite sheet. So if it's an infinite sheet, or this is confusing, but it means you are very, very close. You are very close to the surface. That's going to be the electric field. Very close to the surface, and that will be the voltage for very close to the plane. Is that clear? And here you have a video that will take you step by step if you're interested. So if you have plus, remember that the electric field is sigma over 2 epsilon 0. Okay, it's like a capacitor, for example. Electric field, it's going to be uniform. It does not depend on the distance. But if you have a conductor, like a Van Graaff generator, like this, right? Then electric field equals 0 inside. So at the surface, it's going to be stronger because you cannot have inside. You can do that with Gauss law. Okay, it's just a review. Okay, so you have that, and I recommend that you watch the video. Here, okay, conservation of energy. Are we good? So in physics 1, you have potential energy, which is gravitational potential energy, and then you have gravity, which is like an invisible restoring force that wants to lower the potential energy. If you let go, gravity is going to do positive work. Positive work means it wants to accelerate. So work is positive when kinetic energy wants to accelerate. You let go, and all that potential energy is going to go into kinetic energy. Okay, so conservation of energy says that the change in potential energy will be equals to the change in kinetic energy. Okay, the change in potential energy in that case, we know it's Q delta V. Delta V is the voltage, the potential difference. Okay, the electric potential. Okay, that will be the potential energy because the voltage is the energy per unit charge. We know already that. So now we can use that for finding the speed. Okay, so try to do that. Okay, so you have something at point A, you have a voltage drop from A to B. So A has a voltage of 25 relative to B. So it's like altitude. You start from a high altitude of 25, you place a charge. So the charge wants to go downhill because the electric field is doing work on it. So the potential energy it has uphill will turn into kinetic energy. So you want to find the speed. Okay, so this is like physics 1, same idea. So the change in potential energy equals the change in kinetic energy. So physics 1, it was mg delta h equals 0.5 mass v2 square minus 0.5 mv1 square. Okay, change in kinetic energy. Now we have electric potential energy, which is Q delta V. equals the change in kinetic energy, so 0.5, the mass, V2 square minus V1 square. Okay, that's the voltage drop. So it's always for reference level. So here we suppose this is 25 volt. It's an equipotential 25 volt, and this is 0. It doesn't matter. You can say this is 25 and this is 50. Okay, same thing. You can say this is 25 volt and it's 50 volt. What matters is the drop. It's like altitude. Okay. Okay. So can you compute the speed? So Q, so 3 times 10 to the negative 5. Delta V is 25. 0.5 times the mass. 8 times 10 to the negative 5. So it were released from point, no, it's released from point A. So it means it has no speed to begin with. Minus 0. Okay, so you want to find V2. So what do you get?
9.30.
Yes, 9. Right, about 9. That's Daphne, right?
Yeah.
Did you all find 9?
Where did you get the 0.5 meters from in the change of kinetic energy?
No. Kinetic energy is 1/2 the mass times the speed square. Okay, the mass is in kilogram, the speed is in meter per second, kinetic is in joule. Okay, it's the equation for kinetic energy. It's from physics. It's from physics 1. Yeah, 9 point something. Do we have kinetic energy here? Yes, kinetic energy 1/2 mass speed square. M is the mass and V is the speed. So that will be in your equation algebra based. Okay, so yes. Okay. So the speed is about 9. If I round. So a positive charge will go down the potential. Now, if I place a negative charge and the negative charge is the same coulomb, it will do the opposite. It will go up the potential, uphill, something that goes uphill. But the speed will be the same here, okay, because it's symmetric. Do you agree? It wants, from its perspective, it's losing energy, going up the potential. Positive wants to go down potential. Okay? It's easier to understand with positive. So you think of positive and then you take the opposite. Right. So you have a different way to, maybe your book use that approach. You have a different way to think about it. You can say that the total energy before equals total energy after. So this is conservation of energy. So the total kinetic energy before plus the total potential energy before equals total kinetic energy after plus the total potential energy after. And then you massage it a little bit and you will get the same thing. I think it's a shortcut if you just say, if you just write it this way, okay? Because the change in potential energy is just Q times the voltage drop, okay? Because voltage is energy for 1 coulomb. But you can do it this way. It will be the same thing.
Wait, I'm
Yes.
still confused on the kinetic energy part. Can you do the math for that part again, please?
So the kinetic energy. So kinetic energy is 1/2 the mass times the speed squared. So the change in kinetic energy is going to be kinetic after minus kinetic energy before. So it's going to be 1/2 the mass, the speed after, minus 1/2 the mass, the speed before. So you factor out 1/2 the mass, 1/2 the mass. That will be the speed after, that's what we want, minus the speed before square. This is 0. So that will be 1/2 the mass, which was the mass, which is 1.8 times 10 to the negative 5 v squared, and that should be equals to the charge times delta v. This change of kinetic energy, you want to write it this way, and usually instead of 1/2 you put 0.5. Yeah, okay. So but be careful, don't do the mistake, don't do v2 minus v1 square. It's v2 square minus v1 square. Okay, 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 okay. So remember, positive charge, high potential, low potential, negative charge, low potential, high potential. Opposite. Okay, let's try to do this one. This one comes from your book, so we can help each other. The only difficulty here is that you have to do in 2 steps. First, you have to find the voltage at point A because of this one and because of that one. And then you want to find the voltage at point B because of this one and because of that one. And then you want to find the delta V, the drop in voltage. Drop in voltage, okay, multiplied by Q, and you have the change in kinetic energy. But first you have to find the voltage at A, the voltage at B, so you can find the drop, the altitude change. Okay, so you can help each other. So find the voltage at A first. Okay, you just add the potential from the 3 and the minus 3. Then you find the potential at B from 3 and minus 3. And then you do VA minus VB. And yes, 10 to the negative 9. Okay, so try to do it. You can help. I mean, you can talk to each other. So the equation is that the change in potential equals the change in kinetic energy. Okay, that we know. Because this is the change in potential energy. So the change in potential will be VA minus VB equals 0.5, the mass, the speed before, which is no, the speed after, right, at B square, and the speed. I should not write speed like this because then you're gonna. So I'm gonna put something like this. It's a speed, okay? This is a speed. So we need the voltage at A, the voltage at B, and you have a charge here, Q, which is placed at A. So it's going downhill. It's like a mountain. It's like a hill. You have a voltage drop. So you have an altitude. So it's going to accelerate from the top here downhill. Okay, so you need to find the voltage drop. You need to find the change in altitude, like the delta H. So first you find the voltage at A. So just apply, right? The voltage at the point P is the sum of all the voltage. So at point A, you have from this one, right? You're going to have 9 times 10 to the 9. And then this is 3 times 10 to the negative 9. Okay. And then you have the distance here, 0.1. And this one is negative. So you're going to have 9 times 10 to the 9. 3 times 10 to the negative 9. And the distance between here and there is, and there was a mistake, 0.1. So you can cross this one, right? 9 and negative 9. It goes bye-bye, 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 bye-bye. You can factor out 3, 9, 27, 27. Okay, something like this. And what do you get? So do it compute at A and then you compute at B. Huh? Yeah. 1350, right?
VB is just negative.
Exactly. And then VB. So this is uphill. So you see, it's uphill. It's not happy. It has a positive potential energy relative to far away. It's not going to be happy. It wants to get out of here. And if you do the same computation for B, okay, you're going to get negative 50 volt. So you go from uphill and then you get into the well. Do you agree? Okay, for VB, you have the same. See, you have a 0.01, and from that distance here is 0.02. Do you agree? Okay, so you have delta V. Okay, delta V. Okay, delta V means a drop. By how much you are dropping? So VA minus VB. So delta V equals 0.07 to, okay, 2700 volts. Because it's above the ground, below the ground. So then you're gonna apply these equations here. And except it's confusing because this is a speed. We have the speed. So you have Q delta V equals the change in kinetic energy. So that will be the speed square minus at A. And that will be 0 square because it starts from, no, B. This is at B. The speed at B. And 0 square because it starts from 0. Right? Because it's a V. I should have called it S. I don't know. Okay, so Q is 2 times 10 to the negative 9 and then you have the voltage drop, and then you have the 0.5, and then you have the mass, which is 5 times 10 to the negative 6, and then you have the speed square. So I don't know because I didn't do it. What is Q? Q is 2 times 10 to the negative 9, okay, times 2700, okay, you multiply by 2, okay, and you divide by the mass, so divide by 5 times 10 to the 5 times 10 to the negative what? 9, okay, and you take the square root. Did you get 23? Here it's not a 6, it's a 9. I'm just blind. Did you get that? Huh? I divide by 2. Okay, no, so it's bad. I should I multiply by 2. Multiply by 2. Okay, thank you. 46. Okay, do you agree? So for test number 2, always a question about that. You just have to apply. It's very simple. Change in potential energy equals the change in kinetic energy. Because you have a lot of application. For example, when you have, so this is called a cathode ray tube. That's how they discover the electron, but it used to be used as diode. Okay, in the very old computers, they use that. The first digital computer, they use that to control current. Okay, you go, you don't go, you go, you don't go. So 0110011. It was very bulky. They use that in the old analog TV. If you have grandparents, they have those huge TV, huge one. I don't know if anyone has that anymore, but the idea is that it's a vacuum and you apply a very huge voltage. So, for example, if you have 100,000 electron volt, okay, so the electron will have potential energy of 100,000 electron volt. All that energy goes into kinetic energy, and then it will miss it, and it has momentum, so it will keep going. And here you can make an image if you scan the screen. So it's a vacuum tube. That's how they made X-rays. That's how they make X-rays today. Okay, so you apply a huge voltage, the electron will accelerate, and then it will keep going. It has kinetic energy, and all that kinetic energy goes into X-ray. So if I take the slide from my other class, my baby class, see my baby class here? So you have a vacuum tube here. So this is negative, this is positive. So the electrons here have a huge potential energy, let's say 50 kilo electron volt, right? Huge potential energy goes into kinetic energy, and then they're gonna hit a very heavy metal target, okay? something happen inside, and all that kinetic energy will turn into X-ray. So each X-ray, the photon has the energy of this electron, which is the potential energy. Okay, so you can control the energy of the X-ray by controlling the voltage. So you have soft X-ray, and hard X-ray. Okay, so a lot of applications, we talk about that, like proton therapy for cancer is very, very efficient, except insurance. They don't want to pay for it, but it's better than X-ray because they don't do as much damage. But the idea is the same. You apply a voltage, okay, the potential energy will be Q delta V. So Q will be the proton times the voltage. Potential energy turns into kinetic energy. All that kinetic energy will destroy the tumor. All that energy will be delivered to the tumor, except it won't destroy the healthy cells on its way inside the brain. When you are using X-ray, what they do in radiotherapy, they're using X-ray because X-ray is super cheap and they can charge you a lot, but you are destroying the healthy cells. That's a tangent. I apologize. Let's go back to physics here. Okay, so voltage. Okay, we talk about voltage. So the energy of 1 coulomb relative to very far away. So now we're going to talk about electrostatic energy, which is not the same. So when you say electrostatic energy will be the energy of a configuration, of a distribution of charges. So if you have, so in that case, it's easy. You take Q1 and it takes no effort. Okay, Q1, you just place it here. There is nothing for you to do. And then if you take Q2, you have to do what? You have to push it. All the work that you are doing will be called the electrostatic energy of the configuration, both of them. So in that case, it will be just K Q1, Q2 over R. If you have a negative charge, so then it will be the opposite. The work that you have to do will be negative because it wants to go on its own. So you have to, don't go that fast. So that potential energy will be negative. Why is it negative? Because it's binding. It's happy to be here. It wants to go even closer. Okay, so now if you have a configuration of charges, okay, so don't confuse the potential and the electric energy, the electrostatic energy. So the electrostatic energy, if you have 3 charges, you're gonna use that equation. So that will be the energy that you have to do to place those 3 charges. So it will be energy of the configuration. However, the potential, you see, it's not the same equation because the potential will be at one point, at a given point. So you use this equation. So let's take an example, it's easier. So for example, if you have a water molecule, okay, and hydrogen, oxygen, and you know that if you want to break water apart, you need to provide energy. So you can use electrolysis, right? You have water, you have 2 electrodes, you have a voltage, and then water will break into hydrogen and oxygen. So you have to bring energy to break it apart. So that means the configuration has potential energy. So any molecule in chemistry has potential energy. That potential energy is negative because it's bound together. And if you want to break that molecule, you have to bring some energy. Okay, you have to force it. So let's find the potential energy of the water molecule. So in that case, you're going to use this equation here. Okay, and this means that will be the energy that you have to do, the work that you have to do to get to this configuration. So you say voltage at one point, but you say electric energy of a configuration. So it's not the same equation. So this is the electrostatic energy of configuration. This is the potential at one point. We are not using the same equation. Okay, so let's just do the equation. Apply these equations here. Just plug it in. That will be the potential energy of a water molecule. We just plug it in. Plug it in, plug it in. You see potential energy. So this is a proton because this is hydrogen. This is hydrogen. This is oxygen. So oxygen has 2 electrons. I mean, it's stealing. It's a dipole. It's stealing 2 electrons. Plug it in. Help each other. So Q1. So you can call this Q1. Why not? And you can call that Q2. And you can call that Q3. So Q1 is 1.6 times 10 to the negative 19 coulomb, which is also equal to Q2 because this is the electron. I mean, the proton. That's the charge of a proton. And Q3 is going to be minus 2 times the fundamental charge. Okay, and you are using the equation. It's going to be K. And then you have Q1, Q2 over R12 plus Q2, Q3 over R23 plus Q1, Q3 over. Okay, so that will be the potential energy of the configuration. The energy that you need to provide to bring them together, to bind them together. So plug it in, plug it in, plug it in. So we'll be between this and this, that and that, and that and that. Keep E for, so you don't have to deal with the scientific notation to begin with. So you keep E, and here you keep minus 2E when you start the computation. So do it more you do here, less you have to do at home. Okay. Q1, Q2, Q1, Q2. So that will be E squared over 0.16 times 10 to the negative 9. Q2, Q3. So those two here. So that's a minus. So this one. And the distance is 0.1. And then what? Another one. Okay. So you can do some aesthetic here. Let's do some aesthetic. So 9, this is a 9 times 10 to the 9. I can factor out E squared. So I'm going to factor out. Here I can factor out this. So 10 to the negative 9. And then I have E square. And then here I have, no, E square is gone because I factor out. And 2 and 2 is 4 over 0.1. Looks better. Okay, and you have E is 1.6 times 10 to the negative 19. So you have to plug in it. So that will be 10 to the 18. You have to square that. Do you get that? One point six times 10 to the 19 square. Okay. Divide by, open the parenthesis, 10 to the negative 9. Boom. No, divide by 10 to the negative 9. I'm not sure. Did you get that? Because I'm not sure, right? Before I found minus 8 times 10 to the negative 18. So negative what? 7.8? So I did something wrong. So minus 18 joules. Okay. Maybe it's a 1.6. I don't know. But that's the answer. And the potential energy is negative. It means it's bound. It's bound. So it means if the potential energy is negative, it means if you want to break it apart, you need to provide energy. You need to provide that amount of energy to break a water molecule apart. Make sense? So it's in chemistry. What did I do? Yeah, I combined minus 2 and minus 2 over 0.1. So minus 2 and minus 2 is minus 4. Maybe if you don't simplify, because I'm playing, so if you don't play like I'm playing, you get the answer better.
Yeah, the things pause for pauses. Like I put out the game.
Okay, maybe it's easier if you do it step by step. So make sure did you get that? Huh? Make sure you do it with your calculator. Agree or not? Okay. So that is called the electrostatic energy. So it's not at a given point. Voltage is at a given point. Electrostatic energy is that a configuration, the energy of a configuration. So when they talked, at some point they were talking about hydrogen, the hydrogen industry, the hydrogen economy, because, hydrogen is cleaner, right, than gasoline. Except that to make hydrogen, obviously, you need to break water, and to break water, you have to have energy. So it's not very, very cheap or very environmental friendly. So yes, so that will be the energy. So it's binding. Okay, so this is called the electrostatic energy. Okay, so we already did that. That will be for next pop quiz. So this is a demo that I used to do, but I forgot the fluorescent lamp. So if you have a fluorescent lamp here, you need a very high voltage, like 1,000 volt, for example. So what's happening when you apply a voltage of 1,000 volt, inside you have electrons, and the electrons will accelerate, okay, from the high voltage to the ground. And what is cool, when you bring a fluorescent light close to Van Graaff is like 100,000 volt. Your hand is connected to the ground. So that will be 0 volt. Okay, so this is the ground, 0 volt. That will be 1,000 volt or 100,000 volt or 600,000 volt. So the electron will accelerate, and then it will react with mercury inside, and then it will emit light, but it will be lit between your hand and there. So it's a cool demo. I used to do it, but I forgot the fluorescent. I forgot. Eh, Okay, so so I don't like my voice. I'm gonna close that. So you have your plasma globe. You remember, you can visualize the electric field. This is very high voltage. I forgot how much, maybe 1,000 volt, 100 volt. It's a Tesla coil inside and a capacitor. So it's a very cool thing because you start with only 5 volt from your computer. And then anyway, blah, 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 blah. So I take this. I don't know if you can see. This is lit and this is not lit because you go from 1,000 volt here, and my hand is 0 because I'm connected to the ground. So electrons are accelerating from here to there, going to the ground, but they're not enough to do any damage. It's a very cool demo. Okay, so lots of application because we are electrical in nature, so it's a lot of charge distribution. We do generate very weak electric field, and if you have like a shark, where is my shark? Here, you see, any living things will generate electric field, but it's going to be very, very weak because we have all kinds of distribution of charges inside us. But the sharks, they have very special, very, very high resolution sensors to detect those electric fields. And that's how they can detect the prey, because they have these sensors here. Okay. I don't know exactly how it works, but I know that it works. And then you have those, we already talked about that. You see, you have these special, like fish. You have two kind of fishes. They do that, but I forgot the name. One is the elephant fish. But anyway, in that case, you see, this is charged positively, this is charged negatively. So it's a dipole. The electric field goes from plus into minus. And when it goes next to something that is a conductor, so something good to eat, the electric field will be stronger. We already discussed that because the electrons that move freely and they reinforce electric field. If it goes through a non-conducting material, like a stone, so not good to eat, then the electric field will be weaker. So it's called electrolocation. If you work in electronics, all the transistors, it's all about electric field. And it's so complicated. Biology is so complicated, but if you want to deliver like a drug to the brain, so you want that to cross the brain blood barrier, And so you take a nanoparticle lipid because the brain loves fat. That's why we need to eat fat. So anyway, love fat. So the drug is inside and it's going to be charged. You make it charged. And there is a potential difference between outside the brain, inside the brain. So it's going to move through that potential. That's how they do it. You should go into it because I forgot how it works. Heart, of course, it's also an electrical system with everything is about charge, the distribution, polarization, depolarization, polarization, depolarization. Okay, that's how it works. So we talk about that, right? And we are done. Yeah. So that will be for test number 2. Test number 2, okay, maybe, and what we're going to do next. So now that you know about voltage, I think next unit, I don't know what's the next unit. Oh, we have to do capacitors. So it's capacitor, I'm gonna skim through. It's charging and discharging. And if you are going to go into electronics, there is in Dropbox, there is a video that explains more in details charging and discharging. But the idea is very simple. If you take a defibrillator, it's a capacitor. So you have 2 electrodes. Okay, you have 2 electrodes. You connect that to a power supply. See, you have your 2 electrodes here. You connect that to a power supply. This one will be charged positively. This one will be charged negatively. So this is called a capacitor. Right? So I have. Okay, so you have your power supply 100 volt. You have your defibrillator, 2 electrodes, positive, negative. You disconnect that. And you're going to have an electric field here between the plus and the minus. So all that energy, all the work done by the power supply to move plus here and to remove the plus from here, all that energy is going to be stored inside the electric field. So you can think of the electric field as a way to store energy. That capacitor is going to hold the charge, but it's the storehouse for energy. And that energy can be burnt out in a very small time. You can control the time. Okay, so you have your capacitor, which is like a defibrillator. Everything will be burnt out inside the heart, which is like a load. And you can control how fast you are delivering energy with a resistor. And the capacitor will be discharged inside the heart, and the idea is to make it work again because this is an electrical device. Okay, so a capacitor is a device to store energy inside the electric field. You charge the capacitor and you discharge the capacitor. So you see, this is an exponential decay. For the heart, you need to use an energy of 200 volt to 1000 volt. So 2000 volt is like 200 EV per electron. Okay, so you have a lot of application. So we will skip